session on block design. Our first speaker is Professor Eric Schoon from University of Antwerp in T&D Science and Industry. He's going to talk about a blocking strategy for orthogonal arrays of strength 2.
Good morning, everybody. May I ask your attention right away for a design problem, which will now be flying in, if all is right. Yes. At first sight, this may seem like an unidentified flying object to you, but that's not quite the case. This structure is an orthogonal array, and what you see here is a rectangular kind of structure. The columns of this structure corresponds to the runs in an experiment, and this is obviously done an 18-run experiment. And the rows of this structure correspond to 5 factors in the experiment. These factors define the settings of some property or whatever it is you are experimenting on. And as you see, each row contains the symbols 0, 1, and 2, and these stand for the settings of the factors. Now, this orthogonal array has a special property. It is of strength 2, and that means that if you take any 2 rows, each combination of the symbols, each of the 9 combinations of the symbols, occur equally often. And this property is nice because it implies that if you estimate the main effects of such an experiment, the main effects are orthogonal to each other. However, it is not the case that if you estimate some interactions, that these interactions are orthogonal to the main effects. Now, thus far, it is not really a problem. You are presented with an orthogonal array, and you may want to proceed right away with doing the experiment. However, the problem I want to draw your attention to is how to divide these 18 runs of the experiments in 3 blocks, in this case in 3 blocks, in general in blocks of size 6. So the problem is how to block an orthogonal array of strength 2 in orthogonal blocks of equal sizes. The title of my talk is accordingly a blocking strategy for orthogonal arrays of strength 2. What can I further tell about this slide? It's a Dutch sky here, but if you have looked around you here, it could also be termed an English sky. My affiliations, the University of Antwerp is a 1-day-a-week job for doing research, and T&O Science and Industry is a contract research organization working for clients who want us to solve their problems and are prepared to pay for the solving of their problems. So it's actually a quite nice combination of 2 separate jobs. Here are the contents of my talk. I first want to discuss with you some mostly existing optimality criteria to judge the quality of orthogonal arrays of strength 2, and also to judge the quality of a blocking arrangement of such an array. Then we will see that if we have available an ordered design catalog of orthogonal arrays of a given set of factors and number of runs and level of the factors, then we can use such an ordered catalog fruitfully by looking for a suitable blocking arrangement. And inevitably, I will wrap up with some conclusions at the end. Let's now look at the optimality criterion, the main optimality criterion I want to use to judge the quality of the orthogonal array, not regarding the blocking. I will use in the rest of my talk the so-called generalized word length pattern. Suppose that the array has n factors, then the generalized word length pattern is a vector of length n, and the pth element of this vector is the sum of squared and standardized inner products of a q factor and a p minus q factor interaction. So, for example, if you look at the third position and you consider what is the meaning of the words of length of the figure at that third position, it tells you something about the aliasing, about the, for example, the main effects and the two-factor interactions, because the main effects are of order 1, the two-factor interactions are of order 2, and together they make up the 3, and the 3 corresponds with the third position of this vector. Now, orthogonal arrays all have, of strength 2, all have A1 and A2 equal to 0, so the first really interesting figure is in the third position. Oh, I forgot to mention likewise, if you consider what exactly would be the meaning of A4, it's a kind of aliasing between elements of two-factor interactions and other elements of other two-factor interactions. So it greatly resembles the perhaps more familiar ordinary word length pattern of fractional factorial designs, of regular fractional factorial designs. And in fact, it is a generalization to irregular designs, to any kind of irregular design. And it also happens to be, but perhaps this is a less interesting feature at this moment, a generalization of a special kind of word length pattern, I think by Deng and Tang, called the G2 aberration. So the reference of this generalized word length pattern is in an annals paper of Jeff Wu and Hongxiang Zhu of 2001. Let us apply this, or let us calculate the generalized word length pattern for the introductory example. If we include the blocking factor, we have to do with a 6-factor design, because we started with a 5-factor design, each of the factors having 3 levels, and we added an orthogonal blocking factor, so we end up here with 6 factors of having 3 levels. If we include the blocking factor as a kind of treatment factor, then there are 13 words of length 3 and 13.5 words of length 4 in the generalized word length pattern. That's an odd feature of the generalized word length pattern, that you can have non-integer numbers in the position of the vector. If we only look at the treatment design, so excluding the blocking factor, we have to do with a 5-factor design, and this design has 5 words of length 3 and 7.5 words of length 4. Now there's a little problem, because none of you may have had coffee, but we have to do a little arithmetic now. It's called subtraction. And here's the result. If we subtract these vectors from each other, we arrive at a vector with 8 elements, the first element being 8 and the second element being 6. Now, what does this mean? There are 13 3-letter words in the 6-factor design, so including the blocking factor. There are 5 3-letter words in the 5-factor design, and the difference of 8 three-letter words must be the words that include the blocking factor and 2 other factors. So this 8 corresponds to what I call A21. 2 corresponds to 2 treatment factors, and 1 corresponds to the blocking factor. So you could say it is a TTB word, 2 letters letters of the word corresponding with treatment factors and 1 with the blocking factor. And this number of 8 thus gives us the aliasing between the blocking factor and components of 2-factor interactions. Components, that is, of 2-factor interactions involving the real treatment factors. And by analogy, the 6 4-letter words come by subtraction tell us something about the aliasing between the blocking factor and contrasts denoting 3-factor interactions. But generally these are considered less important. So A21 and A31, as denoted here, tell us something about the confounding of the 2-factor interactions and 3-factor interactions with the blocks. Let's now look at the optimality criteria for blocking and not for treatment factors. Suppose that there is hope that we can recover the information between the blocks, the interblock information. And please take a look at this perhaps strangely looking kind of formula which is there. The entry TTT stands for 3-letter words including treatment factors only, pure words. And the expression TTT is much smaller than TTTT, means that we first want to minimize the number of 3-letter words, pure 3-letter words, and conditional on that, we want to minimize the number of pure 4-letter words. And only after that, I will proceed, only after that we will want to minimize the TTB words. These are the words that correspond with the aliasing between the blocks and 2-factor interactions. Because if we have hope to recover these 2-factor interactions, this between block information, it is less important to minimize TTB than TTTT. So, as a first kind of optimality criterion, we would want to obtain a design in which the order indicated is the order of importance for the minimization of the words in the generalized word length pattern. Now, suppose, on the contrary, that there is no hope whatever to recover the interblock information. In other words, if there are TTB words, and if there are many of them, there is no hope to recover 2-factor interaction information because it is aliased with those hopeless blocks. In that case, we still want first to minimize the pure 3-letter words, TTTT, and subsequently want to minimize the TTB words, the aliasing between the blocks and the 2-factor interactions. And only later on, we want to minimize the pure 4-letter words with only the treatment factors. So as a second optimality criterion, we could want to adopt the W2 criterion. Now, there is still another plausible criterion possible, Suppose that you want to maximize the confounding of the two-factor interactions with the blocks. At first sight, this sounds silly, but what you win with that is that you free the intra-block, the information within blocks, of two-factor interactions as much as possible. So this optimality criteria may improve your error estimates. I say may improve your error estimates because the context in which these orthogonal arrays are applied often only allow for unreplicated experiments and even fractionally replicated experiments, because not all of the combinations of these factors are there. So you do not often have repetitions in your experiments, and you have to do with only 18 figures and trying to figure out what is going on in that experiment. So as a third criterion, we may want to use the W3 criterion, first to minimize the three-letter words, the pure three-letter words, then to maximize the mixed three-letter words, and then minimize the four-letter words involving only the treatment factors. So we have had now some discussion of a possible instrument to optimize the treatment design, and we also have discussed some optimality criterion of the quality of the blocking. And let us now look at how to apply these notions in an ordered design catalog. Last year I used a program developed earlier to generate all combinatorial non-isomorphic 18-run orthogonal arrays of strength 2. And I ordered all these designs according to the generalized word length pattern. What you see at your right hand are the various types of designs that are possible. You have pure three-level designs in 18 runs. You have three-level designs with an added two-level factor. And you have also three-level designs with an added six-level factor. And the figures here in the table are the number of combinatorial non-isomorphic designs of this type. Now, because you have two-level factors, six-level factors, and three-level factors in all these arrays, you will be able to make blocking arrangements in 2 blocks of size 9, 3 blocks of size 6, and 6 blocks of size 3. And for each cell in the table, I ordered the non-isomorphic designs according to the generalized word length pattern. And this allows for a very simple selection if you look for some suitable blocking arrangement. All three optimality criteria for blocking, as you may remember, insist that first of all the number of pure three-letter words should be minimized. And this is achieved if you we want to arrive at a 5-factor design, and we use a 6-factor design to reach this. We use a 6-factor design, we choose one of the factors as a blocking factor, and we arrive at a 5-factor treatment design. Now, if the 6-factor design projects into the 5-factor design ranked first, 501, then it has done the job of minimizing the pure three-letter words. For one of the results of this catalog is that design, 501, is the unique array which minimizes these three-letter words. Now, the first criterion that wants to minimize the pure four-letter words subsequently is satisfied if the six-factor design, the parent six-factor design, projects into that design 501. And there are three designs in my catalog that have this property, ranked 1, 5, and 8. So if you take any of these designs, and if you take the appropriate column that makes the design project into the five-factor design, then you have fulfilled criterion 1. If you want to adopt criterion number 2, which wants to minimize subsequent to the TTT words, the TTB words, then it is best to start with a parent design with the least possible number of three-letter words, and that is design 601. So if we choose that design, you minimize the confounding of two-factor interaction components with the blocks. If you want to maximize the TTB words, you should choose the six-factor design ranked with the highest rank, so the worst six-factor design to achieve this. So to summarize this exercise, what you see here, the three rows in the table correspond to a particular blocking arrangement. For example, the first row corresponds to a blocking arrangement obtained from a six-factor design ranked 1, and taking one of these the columns of this design to be the blocking factor. The middle column corresponds to the pure 3- and 4-letter words in the generalized word length pattern, and the last column corresponds to the mixed 3- and 4-letter words in the generalized word length pattern. What you see here is that you have the same number of 3-letter words and 4-letter words in the first two designs, and that's a small wonder because both designs are in fact one and the same design, 501. But they differ in the number of two-factor interactions confounded with blocks. Here there are 8 components, and in the first design there are 5 components. So depending on the optimality criterion you want to use, you will want to choose one of these designs for the blocking arrangement. And the last design is really a silly design. You should not use that at all. It's an example of what not to do. Now, very briefly, you can also apply these notions to two-level designs, and there's a particular interesting example here. Suppose you have two-level designs, pure two-level designs in 20 runs. Then it is easy to block these in 2 blocks of size 10, because you take one of the factors, and that's the blocking factor, and your remaining factors, well, these are the treatment factors. But it is not possible to take 2 factors of the original design and combine them to a four-level factor, and then have 4 blocks of size 5. Well, it is possible, of course, but it is not possible to obtain then an orthogonal blocking arrangement. However, it is possible to make a design, 20 run designs with one 5-level factor and some 2-level factors. And here are the number of combinatorial non-isomorphic designs of this type. And we can use these designs to make 20 run designs, pure 2-level designs in 5 blocks of size 4. Now we are in for the conclusions. Last slide. We have discussed the blocking of orthogonal arrays of strength 2. We have classified orthogonal arrays with the help of the generalized word length pattern. We can easily base blocking arrangement on a catalogue, a catalogue that is ordered according to the generalized word length pattern, and then project a parent array in an array with one factor less to obtain a blocked array. I discussed 3 blocking criteria. Oh, and that was it. I have shamefully neglected to mention several references. The only references I mentioned is of Jeff Wu and Hongxian Xu of the generalized word length pattern. And there are several authors who are studying this kind of stuff, but they confine themselves mainly to 2-level irregular designs. That was the last note I had included in my lecture. Thank you.
Any questions or comments?
Could you give us an example of your hopeless interblock recovery in practical terms?
In practical terms, suppose that you have on a shelf 5 large planks of wood, not random at all, it's just what you have on the shelf. Suppose that you are reasonably confident that treatment effects do not depend on the planks of wood, but that there is a large variation between these 5 planks. Then I would say it's rather hopeless to recover 2-factor interactions from such an experiment.
Some interblock information.
You do have some interblock information, but it is very much tied up with differences between these planks. If you would have a large batch of planks and you could sample randomly, there's some hope of recovering this information, I would say.
Your answer there raises the question of random effects.
Right.
What models are normally being assumed here?
I would say that in most of the cases, people, in these small cases, people have a fixed effect model, and they just want to know something about the treatment effects.
Would some designs be better when some factors are random, or some effects are random?
I did not really study that question. The criteria are obviously for fixed effects.
Angela?
In finding your orthogonal arrays, did you search through all possibilities, or did you have some method of building them up through projections?
In making the initial catalog, you mean?
Yeah.
Like this?
Yeah.
I searched through all, yes, you could say I searched through all possibilities.
Okay.
There are some tricks to not to have to look at really all possibilities, but essentially yes.
So, what?
If there's doubts.
Quick
And
question.
your generalized word length pattern, is that a straightforward extension of the definition for 2-level factors to 3-level factors, or was there some, something that could be controversial about the definition?
Well, there is some trick in that if you take the usual word length pattern definition for regular three-level designs, what would be counted as one word there would be counted as two words in the generalized word length pattern. That is to account for the difference between two-level factors and three-level factors. But essentially, well, it's just a sum of squared inner products. And it's not my generalized word length pattern. It's just a convenient instrument to.
Okay, so let's thank Eric once more.